Hello, everybody. Welcome to class. Today we're going to talk about Chapter 1, Section 2 over deductive logic. Logic is the science of reasoning and forms the heart of mathematics. We use logic to analyze the truth of statements and describe how statements relate to one another. A statement is something that is either true or false. A statement like 3 is less than 5 is true. A statement like a rat is a fish is false. Many algebraic statements like 3x plus 5 equals 11 may be either true or false, depending on the value of x. In searching a database, you use the three Boolean operators, and, or, and not, to build a test condition. Only show items for which this is true. As a problem-solving tool, we will be attempting to use the Boolean operators to describe the world. When we use Boolean operators to link simple statements together, we form compound logical statements. First, let's talk about negation, the Boolean operator not. The not operator creates what is called the negation of a statement, one that has the opposite truth value to the original statement. The negation of a true statement is false, and the negation of a false statement is true. The negation of a statement can sometimes be tricky to interpret in plain English. For the systems of logic to work, we will insist that every statement must be either true or false, and if a statement is false, then its negation is true. This is called the law of excluded middle. Consider the statement, Carlos is rich. When asked to give the negation of this statement, most people immediately come up with something like, Carlos is poor, since poor is the opposite of rich. However, there is a wide gap between being rich and being poor. Most people fall somewhere in the middle. Even though these two statements are mutually exclusive, they can't be true at the same time, they are not the negation of one another. Instead, the negation of the statement Carlos is rich is that Carlos is not rich. So we just use the word not to get the negation. Now let's take a look at the Boolean operators and or. The and the or operators link two statements together. An and statement is true if both of the pieces are true, and false if at least one of the pieces is false. An or statement is true if at least one of the pieces is true, and is false if both of the pieces are false. Think of it this way. Consider a club, which we will call club intersection for reasons that will become apparent later. Let's say club intersection lets in people who are young and blonde. Then the club would be filled with only young blondes. No old blondes, no young brunettes. It's a rather exclusive club. Now consider a different club, which we will call Club Union. Club Union will let in people who are young or blonde. More people can get into this club, not just young blondes, but also the young brunettes and the old blondes. You only need to meet one qualification or the other, so it's less exclusive. So for and, both need to be true. For or, either one or the other, maybe both, but you just need at least one or the other to be true. And or statements have an interesting interaction with negations. For example, you may state the negation of it is cold and rainy as it is not cold or rainy. But a statement like it is not cold and rainy would not be the negation. Why? The statements it is cold and rainy and it is not cold and rainy are both false on a cold, dry day. If they were negations, one of the two would have to be true. So you can't just put a not with an and statement and keep it and. You can't just put a not with an or statement and keep it or. What actually happens is that the negation of any statement in the form A and B will actually be in the form A or B. The negation of an and statement has to have a not and an or. The negation of an or statement has to have a not and an and. These relations are called De Morgan's laws. So, for example, the negation of it is cold and rainy is it is not cold or not rainy. We give the not to both pieces, change the and to an or. If it was an or statement we were taking the negation of, we would give the not to both pieces, and we would change the or to and. Let's talk about proof by counterexample. It can be difficult to prove that a true statement is always true. This is why every scientific idea is a theory. From the standpoint of logic, watching a pattern repeat will never be enough to serve as proof. On the other hand, it is far more straightforward to prove that a false statement is false. Just one counterexample, one piece of evidence that goes against the logic of the statement, is enough to show that the statement cannot always be true. Remember, there is no room for usually in logic. Example 1. Mathematics teachers often lament seeing students try to claim that the absolute value of x plus y equals the absolute value of x plus the absolute value of y. Find a counterexample to disprove this equation. Step 1, understand the problem. Like I said, this 4-step problem-solving process does not go away. We come back to it over and over and over again. You'll be very good at the 4-step problem-solving process by the time this class is over. Step 1, understand the problem. We're claiming that the absolute value of x plus y equals the absolute value of x plus the absolute value of y is false. We want a counterexample, specific values for x and y which make the equation false. Step 2, devise a plan. Absolute value is defined by 2 rules, one for positive numbers, leave them alone, and another for negative numbers, make them positive. We'll probably be able to find a counterexample if we look at different combinations of positive and negative numbers for x and y. Got to cover both rules. So here, we're going to take a look at first the absolute value of 3 plus 5 equals the absolute value of 3 plus the absolute value of 5. This is an example where both are positive. We get the absolute value of 8 is equal to 3 plus 5. 8 equals 8. It holds when both numbers are positive. What if both numbers were negative? The absolute value of -2 plus -7 equals the absolute value of -2 plus the absolute value of -7. We would get the absolute value of -9 equals 2 plus 7. 9 equals 9. Both negative, the equation still holds true. But if we try numbers with different signs, say a -3 and a +7, the absolute value of -3 plus 7 would be the absolute value of 4, which would be 4. The absolute value of -3 is +3. The absolute value of +7 is +7. 3 plus 7 gives us 10. 4 does not equal 10. If we try numbers with different signs, the equation breaks down. So there is a counterexample. Step 4, look back at your result. the values x equals -3 and y equals +7 are one counterexample that disproves the statement. You could have come up with any other number of counterexamples that disprove the statement. Chances are it would have been one negative number, one positive number. Otherwise, you wouldn't have come up with a counterexample. But it didn't have to be -3 and 7. It could have been -2 and 10. Could have been 13 and -4. I'm just saying these numbers, and I'm assuming it's going to hold true. Feel free to try those if you want to show that those are counterexamples. Let's move on to example 2. In example 2, 4 cards are spread on a table. You know that each has a number on one side and a letter on the other, but you can only see A, B, 4, and 7. The claim is that every vowel has an even number on its reverse. What is the fewest number of cards that you need to flip over to verify this statement is true? So let's understand the problem and devise a plan. Step 1 and step 2. We see A, B, 4, and 7. I've carried that over to this slide. We have a fairly straightforward game. The statement that we've been given is every vowel has an even number on its reverse. We want to flip the fewest number of cards to prove it. The question is misleading. Instead, we should ask what cards could possibly show that this statement is false. What would be a counterexample to this statement? Because just because let me think of how to put this. Basically, remember that it's impossible to prove a true statement is true. Therefore, what we should be doing is trying to find counterexamples to prove that it's false. So we want to flip over any cards that could satisfy a counterexample. The other cards aren't important. Not even if they could, quote unquote, prove it's true. To find a counterexample to every vowel has an even number on its reverse, we need to find a vowel that has an odd number on its reverse. That would prove the statement is false. So our goal is to look for any vowels to make sure that they don't have odd numbers on their reverse, and any odd numbers to make sure that they do not have vowels on their reverse. The other cards don't matter. In this case, we have one vowel, A, and one odd number, 7. We need to check the reverse of these cards. Again, the reverse sides of the other cards do not matter. Step 4, look back at your result. At a minimum, we must check the reverse of 2 of the cards to prove that all vowels have even numbers on the reverse. It may surprise you that we don't need to see the reverse of the 4. The statement says that every vowel has an even number on its reverse. It does not say anything about every even number having a vowel on the reverse. So we just check the A and the 7. Okay, here's where things get fun. Logic grid puzzles. One tool that logic does have for showing that a statement is true is the process of elimination. As Sherlock Holmes famously explains, once you eliminate the impossible, whatever remains, no matter how improbable, must be the truth. Practically speaking, it is rarely possible to identify, let alone test, every possible option for a scenario. That's why we'll study this idea through logic grid puzzles. A logic grid puzzle is a game where there are a few categories and a small number of possibilities for each category. Each element in one category must correspond to exactly one element in each other category. By process of elimination, we narrow down the possible combinations until only one remains. Okay, let's look at example 3. Tony, Wanda, Ken, and Amanda were elected to the student council. Using the following information, deduce which student is now the president, the vice president, the secretary, and the treasurer. The new vice president lives across the street from Ken. The new president and treasurer are both women. Amanda and Tony helped the new president move last week. Step 1, understand the problem. We have 2 categories with 4 possibilities each. Students, Tony, Wanda, Ken, and Amanda. And offices, president, vice president, secretary, and treasurer. We also have 3 clues that are already nicely organized for us. Step 2, devise a plan. We can draw a grid to compare each student to each position. And I'm going to say right now, whenever we're doing one of these, the grid will be given for you. You're never going to have to know how to come up with the grid. Using the clues, we have to find out which combinations do not work. The process of elimination should eventually leave us with the correct matching of students and offices. Carry out the plan. The new vice president lives across the street from Ken. From this first clue, we can tell that Ken is not the vice president because they live across the street from each other. So we mark the cell where Ken would be vice president as no. The new president and treasurer are both women. We need to make an educated guess about the genders of these 4 students based on their names, but this second clue seems to tell us that neither Ken nor Tony are the president or the treasurer. So Ken and Tony get marked no for president. Ken and Tony get marked no for treasurer. And notice in the Ken row, there's only one open spot. So by process of elimination, Ken must be secretary. So we mark that Ken is secretary. And if Ken is the secretary, no one else can be. So no's for Tony, Wanda, and Amanda. Now we notice in the first row, in the Tony row, the only thing available now is vice president. So we mark Tony a yes for vice president and fill in the no's down the column. Because if Tony is the vice president, no one else can be. Amanda and Tony helped the new president move last week. What does this tell us? It tells us that the president can't be Amanda or Tony. And we already know that about Tony, but we can mark this additional information down for Amanda. Amanda can't be president. And now in the president column, there's only one open spot, which means Wanda must be the new president. Mark her the president. No one else can be. The only thing left, Amanda must be the treasurer. Logic grid puzzles are fun. Looking back at the result, Wanda is the president, Tony is the vice president, Ken is secretary, and Amanda is treasurer. If there's more than two categories, the logic puzzle will become a little messier. However, the process will still work the same way. It just won't be in this one little box area. Example 4. Dave opened a new fitness center downtown, which offers classes on the half hour, 9:30, 10:30, 11:30, and 12:30, each in a different type of exercise. Using only the clues below, determine which class Teresa leads. Clue 1. The 10:30 a.m. class is either the yoga class or Karen's session. Clue 2. Karen's session begins 2 hours before the aerobics session. Clue 3. Sandra's session begins 1 hour before the spinning class. Clue 4. The 12:30 p.m. class is led by Opal. Clue 5. The self-defense class is led by Sandra. So using just these 5 clues, we need to determine which class Teresa leads. Step 1, understand the problem. There are 3 categories with 4 possibilities in each category. There are 4 classes: yoga, aerobics, spinning, and self-defense. There are 4 instructors: Karen, Sandra, Opal, and Teresa. There are 4 times: 9:30, 10:30, 11:30, and 12:30. We specifically want to know which class Teresa leads. Step 2, devise a plan. Here is the table for this logic puzzle. We can see it's a little more complicated than just the one box. We have 1, 2, 3 main boxes. Why isn't there a box here? Well, if there was a box here, it would be matching time with time, and that would be unnecessary. Okay, let's get started. The 10:30 a.m. class is either the yoga class or Karen's session. This tells us that Karen does not lead yoga. So 1 no goes where Karen and yoga intersect. Karen's session begins 2 hours before the aerobics session. This clue tells us that Karen does not lead aerobics, but it also limits the time for each. So Karen's not aerobics. That one's a gimme. But Karen's class must be at either 9:30 or 10:30, or there won't be enough time for another class to start 2 hours later. Because Karen's session begins 2 hours before the aerobics session. So we have to allow time for the aerobics session to be 2 hours later. So Karen must be at either 9:30 or 10:30, so she can't be 11:30, she can't be 12:30. And aerobics has to start at either 11:30 or 12:30, so it can't be 9:30, it can't be 10:30. Sandra's session begins 1 hour before the spinning class. So Sandra's session is not the spinning class. So a no goes for Sandra and spinning. And because Sandra's session is 1 hour before spinning, we can eliminate some times. Sandra can't be the last class because it comes before the spinning class, so Sandra can't be 12:30. And spinning can't be 9:30 because Sandra's class is before it. So spinning can't be the first class. So this is starting to fill in, but we haven't been able to deduce anything yet. The 12:30 class is led by Opal. Well, this is on the nose. We mark that Opal is the 12:30 class, which means nobody else can be, and Opal can't teach at any other time. Still not enough to make any deductions. I should say any other deductions. And we can't even call this one a deduction. It was given to us. The self-defense class is led by Sandra. Okay, once again, this is an easy clue to work with. If the self-defense class is led by Sandra, we'll mark that a yes for Sandra in self-defense. Sandra can't teach anything else. Self-defense can't be anyone else. And we have a process of elimination spot. Karen can only be spinning now because she's not anything else. So we mark Karen a yes as spinning. We mark everybody else a no as spinning. So at this point, we need to use our table to our advantage. See if the information within can give us anything else. We know that Karen teaches spinning. But we also know that spinning is not offered at 9:30, which means Karen can't teach at 9:30. So let's put a no with Karen and 9:30, which leaves only one option. Karen teaches at 10:30. Mark Karen and 10:30 a yes. Mark everybody else at 10:30 a no. We've now looked at every clue and we are not yet at the result. But with all of the new information we have in the table, we revisit the original clues. One of the clues said Karen's session begins 2 hours before the aerobics session. Now we know that Karen's session is at 10:30. And if Karen's 10:30 session is 2 hours before the aerobics session, that means that aerobics must be 12:30. So we mark aerobics at 12:30. None of the other times can be aerobics. None of the other classes can be 12:30. We know that Opal's class is the 12:30 class. So Opal must lead the aerobics session. So a yes goes in for Opal and aerobics. Opal's nothing else. Aerobics is no one else. By process of elimination, Teresa leads the yoga session. And there's more information to gather, more things to fill in, but we don't need to because what was the question? The question was, which class Teresa leads. A lot of work, but we found it. Teresa leads the yoga class. I had to go back because it was so long I couldn't remember if our question was who leads the yoga class or what class does Teresa lead. Would have answered both of them. Okay, thank you for your attention today. Our next class will be going over all of the homework problems from Chapter 1, Section 1, and Chapter 1, Section 2. So please be sure to try and attempt all of the homework problems from those two sections before we meet again. I'll see you next time.